Hi, for this mini lecture, Dexter and I will be presenting on quantum error correction, or QEC for short. To start off, let me explain what is error correction. So in general, there are two phases to error correction or quantum error correction. The first phase is detection. So for example, let's say Alice has this quantum state phi, and she sends it to Bob. So phi is an arbitrary state. We can just express it as A cat 0 plus B cat 1. Now, the problem is, in general, our channels that we use to send quantum states through are noisy. So that means that any state that we send through the channel can be modified by some error. So Bob may receive some modified state phi alpha that has different coefficients for the basis states 0 and 1. So the goal is for Bob to detect that such an error has occurred and follow up with a recovery phase, where given that Bob has detected the error, he wants to recover the original qubit state that Alice has sent. Now, before we move on to the rest of the lecture, for this lecture, we only focus on errors that affect single qubits, and we call them one-qubit errors. So that means that if we have a multiple qubit state, we assume that errors can only affect each qubit independently. Now, for the rest of this lecture, we'll go through four main things. First, we'll introduce quantum error correction in greater detail, and this will include talking about the types of errors that can happen and the challenges that we face when designing quantum error correcting codes. Next, we'll have a quick review of classical repetition codes, and this will lead us to talking about simple quantum error correcting codes that are based on repetition, as in the classical case. Finally, we'll end off the lecture with an introduction to the stabilizer formalism and codes. And so the overall objective of this mini lecture is to present simple examples of quantum error correcting codes and then motivate their construction using the formalism of stabilizer codes. So let's start off with the types of one-qubit errors that can happen. In general, we only consider two types of one-qubit errors. First, there are bit flips. That is, given an arbitrary quantum state, alpha 0 plus beta 1, it might be modified to alpha 1 plus beta 0. Secondly, we also consider phase flips. That is, the arbitrary quantum state can be modified to alpha 0 minus beta 1. Before we continue, let's recall the Pauli matrices. So there are three types of Pauli matrices: Pauli X, Z, and Y. Pauli X is equivalent to a bit flip, so it's represented by this matrix here. Pauli Z is equivalent to a phase flip, and it's represented by this matrix. And lastly, Pauli Y is represented by this matrix, and it's equivalent to I times XZ. Lastly, these three matrices coupled together with the identity matrix form the Pauli group, as long as we scale these operators by plus minus 1 and plus minus I. This Pauli group will be very fundamental to our understanding of stabilizer formalism later on. So crucially, we can think of errors as applying either Pauli X or Pauli Z to our state phi. Now, at this point, you might wonder, what about arbitrary continuous errors? So let's say we have an arbitrary quantum state like this, and maybe it gets modified to some other state, gamma 0 plus delta 1, where gamma and delta are arbitrary coefficients in the complex numbers. To answer this question, we need to first state some assumptions and facts. The first assumption is that any error E is unitary. So if we think of it as an operator, that means that E times E dagger must be equal to the identity. The intuition here is that we can view any error E as just another state transformation or a quantum gate, which have to be unitary. The next fact, which we will not prove, states that phase changes do not matter. So coupled with this assumption and fact, we claim that only bit flips and phase flips need to be corrected in any quantum error correcting code. And the idea behind this claim is that first, the Pauli matrices coupled with the identity span the entire space of 2 by 2 complex matrices. So that means that we can write any error E as a linear combination of the identity, the Pauli X, Pauli Y, and Pauli Z. Next, since the Pauli Y operator is equal to I times XZ, and that means that it's like a phase shift from XZ, and since we know that phase changes do not matter, that means that if we know how to correct for Pauli X and Pauli Z, we can easily correct for Pauli Y matrices errors as well. And lastly, the identity is not an error, so it does not need to be corrected. So we conclude that once we can correct for bit flips and phase shifts, then we can easily correct for any error E. Now, let's move on to the review of classical repetition codes. And the reason why we do this is because simple examples of quantum error correcting codes were inspired by classical techniques, especially in the case of classical repetition codes. So for this repetition code, our goal is to correct bit flip errors. Let's assume that we have this bit. It can be either 0 or 1. And we send it through a communication channel that is noisy. So with probability P, the bit flips. So if it was 0, with probability P, it flips to 1, like this. If the bit was 1, with probability P, it flips to 0, like this. So when we receive the bit on the other side, the probability that we get a wrong bit, or equivalently, the probability that we have an error, is P. And this is in big O of P. Now, using repetition codes, we can reduce this probability of error by duplicating bits, sending them all through the channel, and then recovering the majority bit that happens. So how do we do this? Let's have a deeper look. So first, we suppose that we send some bit alpha and repeat it 3 times. So this is where repetition comes in. If we originally had a bit 0, we will encode it into the code word 000. If we had a bit 1, it would then be encoded to the code word 111. Then, following this circuit diagram, we would send all 3 bits through the noisy channel and receive some 3 bits at the end of the noisy channel here. So, out of these 3 bits, none of them, like there are a few different cases that can happen. We could have 0 bits flipped, 1 bit flip, 2 bits flip, or 3 bits flip. In the recovery phase here, what we would do is we would look at all the 3 bits and choose the bit that happens the most often. So let's say if 2 of the bits were 0 and 1 of the bits is 1, that means that we would pick 0 to be the final bit that was sent. On the other hand, if like let's say 2 of the bits were 1 and 1 was 0, then we would pick 1 to be the final bit that was sent. So this is what we call majority vote. And the probability that we end up choosing the wrong bit is the probability that at least 2 bits flipped in the noisy channel. And this happens with probability 3p squared times 1 minus p plus p cubed. So assuming that the probability p is less than half, then we end up with a probability of error of at most big O of p squared. And this is smaller than p. So in this case, we have reduced the probability of error. And if we wanted to correct more than 1 bit flips, or if we wanted to reduce the probability even more, we can repeat even more times. So instead of using 3 bits, we could use 5, 7, and even more bits. We could also concatenate this code to form larger codes. And this idea of concatenation will be very helpful later on in one of the quantum error correcting codes that we present. So that's the review for classical repetition codes. And we can use ideas from this repetition code to design simple quantum error correcting codes. Before we begin though, we have first state some fundamental challenges that we face when constructing quantum error correcting codes. First, there's the no cloning theorem. And that means that when repeating qubits, we cannot directly copy the states. Instead, one workaround is to use entanglement to sort of repeat qubits that happen. And we'll show that later on. The second challenge is that measurement collapses state. So that means that we cannot directly measure the state of a qubit. Instead, one typical workaround is to measure some properties that do not reveal information about the state. And lastly, the third challenge is that errors are continuous. But as we have previously stated, this is not an issue, and we can deal with simply just correcting bit flips and phase shifts. So one last thing before we begin with introducing quantum error correcting codes, I would like to define some terminology that will help later on in this lecture. So the first thing is the idea of a code word, and that is the encoding of an input state. So for example, in the previous repetition code, we had an input state of 0 or 1, and our code word for that bit would be 000. Or if the input state was 1, then the code word would be 111. So this is our encoding of the input state. The next definition is error syndrome, and this is a measurement that is used to detect an error. So for example, in the previous repetition code, we use the numbers of zeros and ones to detect whether a bit flip happened. Thirdly, we have the definition of a distance, and that is the minimum number of errors needed to transform any valid code word to another valid one. So for example, using the same previous repetition code, our valid code words were 000 as well as 111. So in this case, the minimum number of errors that we had to convert between 000 and 111 is 3, because we will need 1 bit flip for each bit. So that means that the distance of this encoding, of this code, is 3. Lastly, we have the idea of a NKD code. What this means is that this code encodes k qubits into an n qubit code word, where the distance of the encoding is d. So in the previous example of repetition code, we would say that that was a 313 code word, because we had one input state bit and it's encoded into 3 bits, and the distance of the encoding is 3. Okay, so now let's move on to the first example of a quantum error correcting code, and this is a 3-qubit repetition code for bit flips. So as mentioned earlier, we'll take inspiration from classical repetition codes, and the goal of this code is to correct a bit flip error on an arbitrary qubit phi. So the first idea here is to repeat the qubits. We would entangle 3 qubits together. And that is done with this part of the circuit diagram, where we perform a C0 on the second and third qubits based on the first qubit. And what this would do is take a quantum state like this, alpha 0 plus beta 1, and map it to this code word, alpha 000 plus beta 111. So that's our code word. And after encoding the input state into this code word, we would send it through the noisy channel here and receive some quantum state phi 1 here. And afterwards, we would perform some measurements on this state and recover the original state afterwards. So let's see how this is done. First, the measurements that we perform are comparative parity check measurements. So that is that, let's say if our original quantum state that we receive after the noisy channel is this, alpha 010 plus beta 101, that means that we have had a bit flip on the second qubit. So what we would do then is to compare the parities of the first two qubits as well as the last two qubits. And that is performed by this part of the circuit diagram here. So as you can see, it takes a C naught of the first qubit and the second qubit together. And that will be the first ancillar qubit that we have. For the second ancillar qubit, we would perform a C naught of the second and the third qubit. Oops, sorry, this C naught should be here. Like so. So what results is, in S1, when we measure this first ancillar qubit, it gives us sort of the parity of the first two qubits. And in S2, this qubit that we measure will give us the parity of the second and third qubits. So if we analyze the different cases, we would come up with a table like this. Let's take a look at one of the cases. In this case, let's take a look at the case where the second qubit was flipped. It is this row here. So first we start off with this qubit state that we have. We encode it into this state, alpha 000 plus beta 111. In this case, I'm writing out the last two ancillar qubits as well, because we'll use it later on in the recovery stage. Now, after encoding, we send it through the noisy channel. And since the second qubit is flipped, we end up with this state, alpha 010 plus beta 101. Now we perform the first syndrome measurement, and it gives us 1 in the first ancillar qubit, because it takes the parity of the first two qubits and they are either 0, 1 or 1, 0, which gives us a parity of 1. Now we perform the second syndrome measurement, and that gives us 1 as well in the second ancillar qubit. And that is because it measures the second and third qubits, which are 1, 0 or 0, 1. So lastly, based on the result of the syndrome measurements, we will perform a recovery. And in this case, since the syndromes are 1 and 1, that means that an error happens on the second qubit. And so we should flip the second qubit back to get the original qubit. And that is shown here in this table. So to be more precise, we would perform identity tensored with the X gate tensored with identity to flip the second qubit back to normal. Similarly, we can also check that the rest of the cases are correct. So for the case where the first qubit was flipped, we would get a syndrome measurement of 1, 0. And that corresponds to an error of X tensored with identity, tensored with identity. And same thing with the third qubit, which gives us a syndrome measurement of 0, 1. And the error is identity tensored with identity, tensored with X. So one thing to note here is that the error is equal to the recovery, as the Pauli matrices are involuntary. So we can just apply the same error matrix to get back to the original state. One particularly helpful way of viewing this code is the spatial perspective. So this is very important for understanding the stabilizer formalism later on. So we can view our set of possible code words as this space, this square space here. And we can view our syndrome measurements as lines that bisect the space. So in this case, you can view S1 as this bisecting line along the vertical axis, and S2 as this horizontal line bisecting the space as well. And since these lines bisect the space, that means that in each of the four quadrants, there are two code words. Now we can see that this top left-hand corner of the space is our set of valid code words 000 and 111. And each of the other four quadrants are spaces of code words that happen because of an error. So the top right-hand corner is obtained by applying x1 to a valid code word. The bottom right-hand is obtained by applying x2, and the other one is obtained by applying x3. So this is a nice visual perspective of how the syndrome measurements give us different subspaces of the code space. Some other remarks. This 3-qubit repetition code is also a 313 code because it encodes 1 qubit into 3 qubits, and the distance of these encoding is 3. And lastly, note that we have not violated any of the challenges of quantum error correcting codes. In particular, there's no cloning because we only use entanglement, and there's also no measurement of state directly. So we don't collapse the state into a classical state. Now let's move on to repetition code for phase flips. And this is very similar to that of bit flips due to a very simple idea. So that is that bit flips are equivalent to applying Hadamard followed by a phase flip, followed by another Hadamard. So what this means is that we can take the same circuit diagram for the bit flip circuit and simply wrap the noisy channel with Hadamard gates. And then we can simply treat any phase flip that happens as a bit flip. So what do I really mean? If you look at this circuit diagram, it's very similar to that of the bit flip diagram. The only difference is that we added these two sets of Hadamard gates around the noisy channel. And this is nice because it results in a very simple analysis. So this is the analysis table, and let's just work through an example. So let's say we start with this arbitrary qubit, alpha 0 plus beta 1. And suppose that when we send it through the noisy channel, a phase flip occurs on the first qubit. So let's just walk through each step. First, we encode the qubit into this. So we basically do the same entanglement and get alpha 000 plus beta 111. Now we apply a Hadamard gate before we send it through the noisy channel. And with the Hadamard gate, recall that the 0 qubit gets sent to plus, and the 1 qubit gets sent to minus. And that is what we are doing here in the second step. Each 0 gets transformed to a plus, and each 1 gets transformed to a minus. So now we are done with our encoding, and we can send it through the noisy channel. So after sending it through the noisy channel, we end up with this state where the first qubit gets phase flipped. So this should be a plus. So recall that when a phase flip happens, plus gets mapped to minus and vice versa. So that means that here, plus gets mapped to minus and minus gets mapped to plus. Now, after that, you apply yet another Hadamard gate to transform our plus and minuses back to zeros and ones. So that means that minus gets transformed to 1 and plus gets transformed to 0. And now we can perform our syndrome measurements like before. S1 would measure the parities of the first two bits, and S2 would measure the parities of the last two bits. And so for S1, we would end up with 1 in the first ancillar qubit because it measures 1, 0 or 0, 1. And for S2, it measures 0, 0 or 1, 1, which results in 0 in the second ancillar qubit. Now, now that we have done our syndrome measurements, we can simply do a recovery, and that is just applying the appropriate bit flip based on which measurement we get. So in this case, our measurement is 1, 0, which means that the bit flip happens on the first qubit. So we would apply this X tensor with identity to recover the original state. Now recall that in the previous bit flip circuit diagram, our error was the same thing as our recovery here. But in this case, our error is different from our recovery. And that is not a coincidence. It's actually just because we're converting between two different bases due to applying Hadamard gates before and after the noisy channel. So within the noisy channel, we get a phase flip, but outside the noisy channel, like after the Hadamard gates, we would simply view it as a bit flip. That means that our recovery will also be a bit flip. So that's the worked example. One other perspective of viewing this is using like some operator notation. If we focus on a single phase flip qubit, phi, and we measure phi after applying the Hadamard gate after the noisy channel over here, what we will get is, well, phi 2 is equal to hzh of phi, which is also equal to x of phi. And this means that a bit flip happens on phi. Now, similar to the bit flip case, we can also think of this using some spatial perspective. So if we view our set of code words as this square, and our syndrome measurements as S1, S2, as bisecting lines of the square, then we can also see that each quadrant corresponds to a particular set of code words, and other quadrants correspond to applying an error onto our valid code word space. Now, lastly, here's an aside. There is a more elegant way of detecting and correcting bit flips using a Toffoli gate. So if you recall our circuit diagram here, we used two extra ancillar bits and applied this set of C-naughts and correction gates to measure the parity and correct the bits. But we can actually compress this down to just these set of gates. Note that this only corrects the first qubit, but the other qubits might be incorrect. But this is fine because we only require the first qubit to be correct anyway. So with that said, let's move on to a more complex example called the Shor code.
Okay, hi guys, I'm Dexter and I'll be presenting on the Shor code as well as the stabilizer formalism later on. So the idea behind the Shor code is very simple. We want to correct both a bit flip and phase flip error. So by concatenating these two ideas that we've seen previously, we get what is known as the Shor code. And you can see in this diagram over here that the encoding for the Shor code is very similar to the phase flip and the bit flip. If you notice the first part over here, this looks like the encoding for the phase flip encoding, and then this part over here is the encoding for the bit flip, right? Where the bit flip only had 3 qubits, so it's this 3 qubits, but we repeat it 3 times, and we end up with a 9 qubit code. So by following the circuit, what we have is that we are sending zero to a logical zero to um, this state over here, which is basically 3 times like tensor of 0, 0, 0 plus 1, 1, 1, ignoring the normalizing factor. And we send 1 to 0, 0, 0 minus 1, 1, 1 tensored 3 times. So for a general state psi, which we will represent with alpha 0 and beta 1, it will be encoded as such, right? This is the 0, and we just have the alpha coefficient in the front, and then we have the bottom with the extra beta coefficient. So how this works? To detect errors and recover, there are a few implementations, but for this we chose the implementation that we thought was the simplest, which uses a bunch of C0 gates and this Toffoli gates. So the recovery and is as such. We have the bit flip section first, and then we have the phase flip afterwards, the recovery for the phase flips. So, okay, before we run through an example of how this would work, what errors can the Shor code handle? So it can correct one bit flip and one phase flip at the same time. And actually, it can do a little bit more than that. It can correct up to 3 bit flips if they happen on separate blocks. And by blocks, I mean these individual blocks. So if a bit flip happens on the first block, a bit flip happens on the second block, and if another one happens on the third block, it can correct all of that. And actually, this is sufficient to correct an arbitrary 1-qubit error, as we seen just now, but we will show a more explicit construction later. So to demonstrate the correction, we'll be choosing an example where there is one phase flip and one bit flip error. In this case, we are going to choose the phase flip on any of the first 3 qubits, as well as a bit flip on the first qubit, just to show sort of like the worst case scenario. So again, the encoder state looks like this, right, as shown above as well. And when we send it through the noisy channel, for a bit flip, let's say it happens on the first qubit. So the resulting code will look like this. We have the 0 changed to a 1 and the 1 changed to a 0 over here. And for the phase flip, since the state is entangled, this state is entangled, any phase flip on the first to third qubit will change the sign of this from a plus to a minus and a minus to plus over here. So what happens is, after the noisy channel, the state looks like this with the differences highlighted in purple. Okay, so now let's see what happens, right? For the first part, from psi 1 to psi 2, we are going to correct the bit flips. And we're going to look at it from a block by block perspective, right? So if we look at the block, let's say the block has no bit flips, so it was fine, right? It could have a phase flip, which we put there by a plus minus. So if we have 0, 0, 0 plus minus 1, 1, 1, doing C0, right, as shown above over here, we will end up with this state over here, right? The zeros doesn't do anything, and the 1, 1, 1 will flip to 1, 0, 0. And afterwards, we do the Toffoli gate, which doesn't do anything because the second and the third qubit are zeros. And for the bit flip case, so in our example, we consider the bit flip happening on the first qubit, right? So it looks like this. When we do the C0, the second and third qubit over here will flip, but for here it won't because the first qubit is 0. And then when we do the Toffoli, we will flip both of the first qubits from 1 to 0 and from 0 to 1. So already you notice that if we just look at the first qubit, the bit flip has been fixed, right? Originally it was a 1 and a 0, now it's a 0 and a 1. And just to trace the rest of the circuit, even though that's the phase flip part of the circuit, but to show that it doesn't affect our result, we will take Hadamard over here between psi 2 and psi 3. So when we take Hadamard, first of all, we notice that, let's look at this block of qubits here. If you look at the second and the third qubit, they are the same in both of them because they're both 1, 1, right? So what's really left for the first qubit is that it's 0 minus 1, right? And when we take Hadamard on 0 minus 1, of course, with some normalizing factor, we get a 1, right? Because 1 sends Hadamard on 1 will give us 0 minus 1. And so Hadamard on 0 minus 1 will give us 1. So this will give us 1, 1, 1. And for the bottom, it's 0 plus 1, right, on the first qubit. So we get 0 when we do Hadamard. So psi 3 is this. And now we will do C0 on the fourth and seventh qubit using the first qubit over here. Okay, so how does this work? We will be, okay, so for psi 3, since the first qubit is 1, we will flip the fourth and seventh qubit. So they go from 0 to 1. And for the other case, since the first qubit is 0, we don't change anything. So it stays at 1. Okay, and then we apply Toffoli. So this is both 1, so we flip this to 0. So we get 0 over here. And similarly, since this is both 1, we will flip the 0 to a 1. And now you notice at the end that if we look at the first qubit, we have a alpha 0 plus a beta 1. So by extracting the first qubit, we recover our state. And so you can see that the Shor code can handle both a bit flip and a phase flip error, even if they occur on the same bit, right? So now we claim that this is sufficient to correct any single qubit error. We will provide an explicit construction here. So first of all, let's suppose that the first qubit, right, without loss of generality, that the first qubit encounters an error which sends 0 to A0 plus B1 and sends 1 to C0 plus D1. So the state after the noisy channel will look like this. Basically, it's we had originally over here we had a 0, 0, 0 plus 1, 1, 1, but the 0, 0, 0 gets sent to A00 plus B100, and the 111 gets sent to C011 plus D111. And we do the same for the bottom, but of course we have to take note of the negative signs. Now this is the construction. We let K plus M to be A, K minus M to be D, L plus N to be B, and L minus N to be C. And by doing so, we can actually factorize the state psi into this. And what you see here is basically we have four blocks of states. This first block is really just a state with no errors. Of course, we have the K coefficient, but there is no errors here. The L block here has a bit flip in the first qubit. The M block has a phase flip, right? And the N block has both a bit flip and a phase flip. And so we basically showed that for any arbitrary error, it can be decomposed into a linear combination of I, X, Z, and XZ gates, right? And we've shown previously that you can correct all these errors, right? Or more specifically, we showed the example where there is a XZ error on the first qubit. And because this is a linear combination of all of this, we can therefore correct any like arbitrary one qubit error. Okay. So now let's talk a little bit about stabilizer formalism. So what is stabilizer formalism? In a sense, it's a way to really see what the math is behind all the error correcting codes, like what is really going on and how does it work? How does the error correcting codes magically sort of flip the bits in a way that recover your error, right? And the math behind it is basically saying that this at least for this class of codes, the stabilizer codes, what we're saying is that we are sending the errors are sending codes from the code space to different eigenspaces, and then we are sending them back to the original code space, right? And we will elaborate more below. But first of all, uh, just a recap is the poly group is basically this set of finite elements, right? We have the identity, we have the X, Y, and Z gates, along with the plus minus 1 and plus minus I coefficients. And the X, Y, and Z are these gates below. So X gate is the NOT gate, the Y gate is this gate with some I, and the Z gate is the phase flip gate. And if you like, you can check that this is a group under matrix multiplication, right? So for example, one of the, I'm just going to run through one is if you do X and Z, you get this, which is negative IY. So this is closed under matrix multiplication, and you can check for the rest that it really is a group. Another interesting property of the poly group is that the elements either commute or they anti-commute, right? And we won't prove this, but so what does it mean to commute? It means if we take any element in the group, any two elements, call it sigma I and sigma j, either sigma I, sigma j equals to sigma j, sigma I, which means you can flip the order or at which they are being applied, and you get the same result, or they anti-commute, which means that if you flip the order at which they are applied, you get a negative sign, right? So an example here is for zx, if you calculate zx, you actually get this matrix over here, which is I times y. And we've shown above that x times z is minus iy. So actually zx is equals to negative xz, which shows that x and z anti-commute. Because when you flip the order, you get a negative sign in front of them. And for an example of which they commute, we can take the identity because the identity commutes with everything. So ix equals to xi is one example. Now, P is of the poly group is a group of operators acting on one qubit, right? Particularly, they are sort of like a group of one qubit gates. And you can extend this to n qubit gates by taking the n-fold tensor of the poly group, which we will denote by this p to the tensor of n. And this is basically a group with the same properties, right? They have, in particular, they have the property where the elements either commute or they anti-commute, right? And this will turn out to be very useful later on. Now, what is a stabilizer, right? We will now define what a stabilizer is. So for any n-qubit stabilizer, we want to define or we want to have sort of a set of states which are not affected by the stabilizer gate. Right? In particular, if we choose any stabilizer K, then the stabilizer states are all the states psi such that K of psi equals to psi, which means to say when we apply these gates to the state, it doesn't change the state at all. And we call K the stabilizer and psi the stabilizer state. And the idea behind stabilizer code is that we can do this for many stabilizers. So we choose a few stabilizers. We find out the stabilizer states of all of them, and we take the intersection. And this will give us a collection of stabilizers as well as a set of states psi, such that Ki of psi equals to psi for all the stabilizers that we have. So sort of like an example, if we consider a 2-qubit system and we choose our stabilizer x tensor x, so xx, and we want to find our stabilizer state, it turns out there's only two, or rather it's a two-dimensional space. And the states are, as such, we have 0, 1 plus 1, 0, and 0, 0 plus 1, 1. And we can check this. If you take 0, 1 plus 1, 0, and we do x tensor x on it, 0, 1 will be sent to 1, 0, and 1, 0 will be sent to 0, 1. And you notice that you end up with the same state that you started with. And similarly for 0, 0, 1, 1, when we do xx, we get 1, 1 for the 0, 0, and we get 0, 0 for our 1, 1. And we end up with the same state that we started with. Notice how in the 2-qubit system, we started with 4 dimensions, right? If we have 2 qubits, just arbitrary qubits, we have 4 dimensions. But after choosing our stabilizer and considering the stabilizer state, we only end up with 2 dimensions. And this is not a coincidence at all. It turns out that the stabilizers will partition the space into half, which we will show now. Before that, we will just make a small definition of a Hermitian matrix. So a Hermitian matrix is basically any matrix that is equal to its conjugate transpose. And an example would be Hadamard. If you take the conjugate transpose of Hadamard, you get Hadamard itself, right? And also in particular, all the Pauli matrices are Hermitian, right? We can check them since, if you take the conjugate transpose of a NOT gate, you still get a NOT gate. If you take the conjugate transpose of the phase gate, you get the phase gate, and so on. So the claim here is that every element of the n-dimensional Pauli group partitions the Hilbert space, or the space of that we're working with, or the vector space, into 2 equal parts. And these 2 equal parts will correspond to the +1 eigenspace and the -1 eigenspace of that operator that we chose. Right. So a brief proof of why this is true. We borrow some results from linear algebra to help us show this. First of all the Pauli matrices are Hermitian. And same, it goes for the n-dimensional case as well, they are Hermitian. And there is this theorem in linear algebra called the spectral theorem, which one part of the spectral theorem basically says that the eigenvalues of a Hermitian matrix are real. And so that's one part of it. And similarly, we have that the Pauli matrices are unitary, which means that the eigenvalues of them have absolute value of 1. So if we put these two together, if we have the absolute value the absolute value of its eigenvalues be 1 and that they are real, there's only 2 options, right? +1 and -1. But how do we know that they are equally distributed? It turns out Pauli matrices have a trace equal to 0. So, and since the eigenvalues lie on the diagonal of the matrix when we choose the orthonormal basis of eigenvectors, so it follows from that our +1 and -1, there has to be an equal number of it, right? Because if we have more +1s on the diagonal, then the trace would be positive, and same for the negative. So they have to be equally distributed, and the number of these eigenvalues on the matrix correspond to the dimension of the eigenspace. And since they are equal, we have that the eigenspaces are equally partitioned. So example for this, if we consider the 3-qubit system, and we consider ZZI and IZZ as our stabilizers, right? Then we will get this diagram over here. So we start out with 8-dimensional space, and we are going to partition it into 4 individual 2-dimensional spaces. So notice that 0, 0, 0, 1, 1, 1, as well as 0, 0, 1 and 1, 1, 0, these are all the +1 they lie in the +1 eigenspace of the ZZI operator, because if we take ZZI and we apply it to 0, we get 0, 0, 0, 0. And if we do it for 1, 1, 1, we get we will get a negative on the first one, we'll get a negative on the second one, and then they will cancel out, and we will get 1 as well. And you can check that it holds for the others as well. So this 4 vectors lie in our eigenspace for ZZI, and the other 4 lie in the -1, right? So for example, if we look at this 1, 1, 0, if we take Z on the first qubit, we get a -1, and then Z on 0 doesn't do anything, and I on 0 doesn't do anything. So we end up with a -1, which means that it's in the -1 eigenspace. And we can do the same for IZZ and check that when IZZ is applied to these matrices, not these matrices, these vectors, we get the same vectors, right? And when we apply on these vectors, we get a -1 coefficient in front. So they lie in the -1 eigenspace. And by doing so, we see that we partition them into these individual eigenspaces. And for our code word, what we do is that we choose the intersection of the +1 eigenspace as the code space. So by convention, we choose, in this case, the 0, 0, 0 and the 1, 1, 1 as our vector space, vector states for our logical qubits, right? More specifically, we can map 0 to 0, 0, 0 and 1 to 1, 1, 1. So for errors, this is where we use the specific property just now, where Pauli operators either commute or anti-commute. First of all, we note that the errors belong to the Pauli group, since we can always decompose error as a linear combination of Pauli operators, right, on a single qubit. And so if we have a particular stabilizer S and error E, let's see what happens when they commute, right? If they commute, then S E of psi will be equal to E S of psi, which is E of psi, since S of psi equals to psi, because S is a stabilizer of psi. And this means that E of psi is in the +1 eigenspace, right? Because we applied S onto this E of psi, and we get the E of psi back. So E of psi is in the +1 eigenspace. And if they don't commute, so if they anti-commute, then when we flip the order, we get this negative sign in front. Right? Again, S of psi is psi. So we end up with a negative E of psi. And this means that E of psi is in the -1 eigenspace. So you can see that when the error commutes with the stabilizer, it will send the state into the +1 eigenspace, right? And if it anti-commutes, then it will send the state into the -1 eigenspace of that operator. So we take the example from earlier, where we are considering bit flip errors, right? It turns out that ZZI and IZZ is a good choice of stabilizers for bit flip errors, for single bit flip errors. And let's look at the table over here on the left. So we consider a single bit flip error on the first qubit, right? Which is basically XII. And let's look at the first stabilizer, ZZI. Since we have, so we compare the first bit, we have X and we have Z. X and Z do not commute, they anti-commute, right? Since they anti-commute, we have a -1 eigenspace. And then we have I and Z, which commute, and then I and I, which commute. So overall, we are left with a -1 eigenspace. And this is shown in the diagram on the right here, where XII sends the code into the -1 eigenspace of ZZI, right? For IZZ, if you compare it with XII, X commutes with I. So that's fine. We are in the +1 eigenspace. I commutes with Z, and the second I also commutes with Z. So this sends the code into the +1 eigenspace of IZZ, which is over here. And combining these two, we get that the final code will be in this eigenspace over here. And we can do the same for the other errors. And we see that each error sends the code into its own individual separate subspace, like so. And this is exactly what we want. We want to choose a stabilizer that where all the errors that we are trying to correct will send it into other subspaces where we can detect them. What we don't want is if the errors send the code back into the same eigenspace that it started with. We don't want that, because if that happens, then we are not able to detect whether an error has occurred, because it stays in the same space. So in this case, this is a good choice of stabilizers for the single bit flip errors. Now, how do we detect and recover from errors? Right? Previously, we've shown that we can detect errors by seeing which eigenspace they land in. But how do we recover from it? So notice that the Pauli operators are Hermitian and unitary. Hermitian means that the matrix is equal to its conjugate transpose, and unitary means the conjugate transpose is equal to the inverse. So if we combine those two together, we get that the matrix is its own inverse, which means A squared equals to I. So to undo an error or to recover from an error, we simply need to perform the same operator on the specified qubit. A simple example would be if we had a bit flip in the second bit, we just need to perform the bit flip on the second bit again, and that will give us our original state. So the key idea here is that drawing example from earlier with the bit flip example, the key idea is to basically do some sort of parity measurement to identify what kind of error as well as the position of the error. Because once we know those two information, we are able to simply perform that same error operator on that specific position, and we can recover from the error. So we can apply this to the 3-qubit phase flip. So if we naively use the same stabilizer as previously, where we chose ZZI and IZZ, let's see what will happen, right? So a phase flip error, a single phase flip error is represented by a Z gate. So if we have a phase flip on the first qubit, it looks like this, ZZI. And consider it when with the ZZI stabilizer, right? We notice that, well, first of all, Z commutes with Z, since everything commutes with itself. And we have I commute with Z, and I commute with Z. So this error sends it into the +1 eigenspace. And we can repeat for everything else, and we notice that all these errors send the code back to the +1 eigenspace. which is shown in the diagram on the right over here, right? And this is bad because when the error occurs, the code just gets sent back into the same eigenspace, which we cannot detect. So this is clearly a bad choice of stabilizers. So we want to choose a different set of stabilizers that can actually detect the error. So instead, let's consider these stabilizers, IXX and XXI. First of all, let's note that when you do a NOT gate on a plus operator, we get back the plus operator. And if we do it on the minus operator, we get a negative minus operator. So let's consider maybe let's consider the phase flip on the first qubit. So comparing the first bit, we have Z and I, which commutes. We have I and X, which commutes. And we have I and X, which commutes. So this sends it to the +1 eigenspace. As for the XXI operator, X and Z does not commute. So we have one negative one eigenspace. I and X commutes, and then I and I commutes. So overall, we land in the -1 eigenspace, which is represented over here. Over here. Over here. And similarly, we can check for the other errors, and we will see that they send each error to a different eigenspace, which is exactly what we want. Right? This way we can detect the errors. And the key thing to see here, or something to note here, is that these stabilizer states are not exactly in the computational basis, but rather they are in the plus minus basis. So in this case, we want our code word to be in this +1 eigenspace. So we map 0 to the plus 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 state, and we map 1 to the minus 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 state, right? So we choose our 0 logical to be this, and our 1 logical to be this, right? In other words, we will send our 0 to this at the start to encode it, and we'll send our 1 to the minus 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 to encode it. And you notice that this is precisely what was done in the 3-qubit phase flip code, right? We started with alpha 0 and beta 1, and we encoded it into alpha plus 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 beta minus minus minus. So to recall the table earlier for what we did for recovery, this is slightly different, but the idea is the same. And the key point to notice here is that, first of all, the error and the recovery operation is the same, right? Because they are Hermitian. Once we know the position of the error, we can simply repeat the operator onto that particular qubit and we will recover it. So you notice that the error and the recovery are the same. Secondly is that this matches exactly the stabilizer point of view of our Hilbert space, right? In particular, if you see, for example, the phase flip on the second qubit, which is represented by IZI, then we get the error in this state here, psi1, which is plus minus 1, alpha of plus minus 1 plus beta of minus plus minus, which corresponds exactly with the stabilizer state, right, in this eigenspace that IZI sends it to, right? All right. Lastly, we will want to talk about some other details about stabilizer codes. So notice that when we have k logical bits and n physical bits, we need n minus k stabilizers. So k logical bits is basically how many qubits we want to encode, right? In this case, or throughout this all these examples, is that we have one logical bit because we want to protect one qubit, and we use in the case of the 3-bit repetition code, we use 3 physical bits, so n is 3, which means we need n minus 1 stabilizers for the 3-bit repetition code, which we did, right? We chose IXX and XXI. Now, why is this the case? So this again comes down to how the stabilizers work. So fundamentally, when we have n physical bits, we are really working in a 2 to the n dimension qubit space, right? And each stabilizer partitions the space into half. We basically cut the space into half, and so we go from 2 to the n dimensions to 2 to the n minus 1. And of course, what ends up happening is we choose the +1 eigenspace as our code space. So if we want a 2 to the k dimension logical space, which is basically the number of bits or that we want to, the number of dimensions we need to store our qubit, then we need n minus k stabilizers, right? Just because to cut the 2 to the n space, we need to cut it n minus k times to get 2 to the k. And lastly, the Shor code also happens to be a stabilizer code, right? And in the Shor code, recall that there are 9 physical qubits, and we are trying to protect one logical bit, which means we need 9 minus 1, which is 8 stabilizers. And indeed, these are the stabilizers for the Shor code, right, given below. And maybe as an exercise, you can try to figure out, or I guess it's already written out, but check that the +1 eigenstate vectors are precisely what is shown in the Shor code, which is the threefold tensor of the 0, 0, 0 plus 1, 1, 1, as well as the 3 times tensor of the 0, 0, 0 minus 1, 1, 1. And yeah, with that, we've come to the end of this mini lecture. So to conclude and to summarize, we've introduced sort of the types of errors as well as the challenges faced with them, including like the no cloning theorem, the fact that errors exist on a continuous spectrum, and that measurement collapses the states. And then after that, we went with introduction to classical repetition codes, which gives us inspiration for how quantum repetition codes can sort of mimic the classical version. And from there, we extended onto the Shor code, which is just a concatenation of the 3-qubit repetition code for the bit flip, as well as the 3-qubit repetition code for the phase flip. And from there, we talked about how this is sufficient to correct any arbitrary 1-qubit error, because arbitrary error can be expressed as a linear combination of X and Z gates. And afterwards, we talked about stabilizers, which is basically a more mathematically formal way of viewing how error correction really works. And the real reason behind it is that we are working in a qubit space, and we are sort of partitioning the qubit space into its individual eigenspaces, and we choose one of them to be our code space. Then we have the errors sort of bring the code words or the code space into other eigenspaces, which we can detect and then bring it back to the original code space. So with that, we've come to the end of our mini lecture. We hope you enjoyed, this mini lecture, and yeah, we'll see you next time.
Nice.